Hello friends, welcome back. In today's session, we will talk about electronic configuration of multi-electron atoms. The session is planned as follows, that is, to begin with, we will briefly review what we did in the previous session. Thereafter, we will talk about the energy levels. We will talk about energy levels first for hydrogen atom, thereafter we will talk about the multi-electron atoms over there. Then we will try to see how are the two different there. Then we will come down to the electronic configuration, that is the distribution of electrons amongst these energy levels. In this context, we will talk about the rules which determine them and also bring in the experimental determination of electronic configuration of atoms. Thereafter, we will take up certain anomalies over there, that is certain electronic configurations which do not kind of confer to these rules. And in this context, we will bring in the concept of the extra stability of half filled and fully filled orbitals of a given subshell. We will discuss in detail about that. Let us recall what we did in the previous session. In the previous session, we primarily discussed hydrogen-like wave functions, and in this context, we described the radial wave functions and explained their significance. After that, we talked about angular wave functions and explained their significance in determining the shapes of the orbitals there. And then we explained the shapes of simple orbitals like 1s, 2s and so on and so forth. So, that is all what we did in the previous session. Now, let us move further. And before we go further, let us talk about one more recall over here. That is, if you remember that when we solved Schrodinger wave equation for hydrogen atom, we got three things. First one was a series of wave functions, r wave functions, theta, phi and so on and so forth. Second thing we got was the quantum numbers and the interrelationships between them. And the third thing which we got, the important thing was the expression for energy of electron in hydrogen atom. That happens to be En to be equal to minus 2 pi square mu z square E4 by n square h square. Now, out of these three outcomes of solving Schrodinger wave equation, the first two have been dealt with in details, because in the previous session we talked about the wave functions, interpretation of them, and prior to that we discussed about the significance of quantum numbers also. Now, let us move on to discussing the third outcome of solving Schrodinger wave equation, that is the energy expression. The energy expression, as I just mentioned, if you note it carefully, that this depends only on one quantum number, that happens to be n, the principal quantum number. There is nothing like L or ml over there. That means the energy depends only on the principal quantum number. And if you see it carefully, we have a negative sign here, pi, mu, z, E and h, all are constants over there. So, essentially En, the energy of the nth orbital, is proportional to minus of the some constant over here by n square there. It is inversely related to the square of the principal quantum number there. That is one general observation we have from the expression here. Now, if you just see what does it mean when you say it depends only on n, essentially it means that the orbitals of a given principal quantum number are degenerate, because when you have certain value of n is there, then if you got corresponding values of L and ml are there. That means a given n can have number of orbitals in that, and all of them will have the same energy. That is the meaning of this statement here. Now, if you look into little more details over there, so the energy of orbitals in case of hydrogen atom would be something like this. So, 1s will be less than 2s, which will be equal to 2p. That means this is for n is equal to 1, these two are for n is equal to 2, these three orbitals belong to n is equal to 3, and these are for the n is equal to 4 and so on and so forth. That means within a principal quantum number, all orbitals will have the same energy. This whole expression can be shown in terms of an energy level diagram. That means typically the energy level diagram for hydrogen atom will look something like this. This is the 1s orbital there, then 2s and 2p are degenerate, 3s, 3p, 3d are degenerate, 4s, 4p, 4d and 4f are degenerate there. Now, that is the energy level diagram for hydrogen atom. And if you move further, because our interest primarily lies in the multi-electron atom, because for hydrogen atom there is only one electron, it occupies only the 1s orbital if it is in the ground state. If you give more energy to that, it will go to one of the higher energy levels over there. But the issue comes up is when you talk about multi-electron atoms, what happens there? Now, when we extend our argument of say the quantum mechanical treatment of hydrogen atom to larger atom having more than one electron, we find that the shapes of orbitals remain roughly the same as we have in case of hydrogen atom, but the energies of these orbitals are changed, and that actually happens because of the presence of more than one electron over there. We will discuss in detail as we move further later. As a consequence, what happens? Our energy level diagram for a multi-electron atom would change. That will look something like this. What you find from here is, that is, 1s remains where it was, 2s and 2p, which were degenerate earlier in case of hydrogen atom, the degeneracy is lifted. Similarly, for 3s, 3p, 3d, degeneracy is lifted. This also is same is true of 4 and so on and so forth. Now, what you see is that energy depends on n and L both. That is one typical deviation from what we had in case of hydrogen atom. In case of hydrogen atom, energy depended only on n, but now the energy depends on the principal quantum number and the azimuthal quantum number. Now, if you go further, for a given value of n, that is for a given principal quantum number, the energy of an orbital increases with increasing value of L. Let us take the example here, say 3s orbital, where n is equal to 3 and L is equal to 0. This is having energy lesser than that of 3p, which has got n is equal to 3, L to be equal to 1, which is further less than that of the 3d. That means, within a given principal quantum number, the energy depends on the azimuthal quantum number there. That is with respect to our multi-electron atoms there. Same diagram, so called energy level diagram, can be shown in this particular fashion also. This is an alternative representation of the same expression over there. Now, what you see from here is, this also shows that there is the degeneracy of the second n is equal to 2, n is equal to 3 and so on and so forth levels are lifted in this case. But what you see from here is, this kind of representation essentially are generalized diagrams. That is, if I want to talk about energy diagram for say helium atom or lithium or maybe sodium atom, or we go to potassium, so you find that energy disposition will be something like this, but actual energies will be different over there, because in that case there will be more number of electrons there, and accordingly the intricate values of these energy levels will be different, but roughly this kind of a sequence remains the same, by and large remain the same. Let us ask ourselves that what determines the order of energy levels. The answer to that is, the energy of an electron in a multi-electron atom is determined by the electrostatic interaction of the electron with the nucleus, which is attractive interaction, which decreases energy, and the repulsive interaction with other electrons there. Let us understand this. Suppose I have say a lithium atom. In case of lithium atom, there are 3 electrons. So, how are they distributed? We have a nucleus which is positively charged. We have got 1s orbital which contains 2 electrons, and the 2s orbital which contains 1 electron. Now, if I am trying to focus my attention onto this 1 electron, the valence electron of lithium atom, which is in the 2s orbital there. Now, this electron feels some kind of attractive influence from the nucleus, that is a stabilizing force, and also this feels some kind of a repulsive interaction from the 1s electrons there. Or maybe suppose we had a case of a beryllium, there were 2 electrons in the 2s orbital there. So, they can also have mutual repulsion to each other. So, the total energy of an electron in an atom depends on sum total of all these interactions, which are attractive or repulsive there. Okay. Now, in addition to all this, in addition to these electrostatic interactions, there are 2 more effects there. One is called as a shielding effect, and second is called as penetration effect. Let us understand these 2. Now, if you look at this picture, this gives you radial probability distribution curves for 1s, 2s and 2p orbitals there. So, what you find is that on an average 1s electron is quite close to the nucleus there, 2p on an average is somewhere here, and 2s is somewhere here, which is very interesting to note that 2s is slightly farther from the 2p orbital there. That means the electron in this orbital will be slightly farther from the nucleus. But what you see from here is, if any electron is occupying say 2s orbital or a 2p orbital, will have electrons occupied into the 1s orbital over there. Since 1s orbital is much closer to the nucleus, so there is nucleus there, there is a 1s orbital there, 2s is somewhere here. So, these electrons which are occupying the 1s orbital, they shield these electrons, the outside electrons, from the nuclear charge there, because if these electrons are not there, 1s is not there, this nucleus will interact directly with these electrons there. But since as now we have got 1s electrons to be there, so they shield this nucleus. This is called as shielding effect. And what you find is, as a consequence of the shielding effect, as I just mentioned, the 1s orbitals shield the outside electrons over there. Okay. This is one factor which determines the order of energy levels. So what kind of shielding is offered by the inner electrons, that is going to determine the energy of the outer electrons there. The second more important effect, what is called as a penetration effect. Now, if you look at the same diagram again slightly differently now, what you see is that suppose I am talking about say 2s electron or a 2p electron. What you find is that 1s is right there, fine. Now, if you look at the distribution of this 2s, the radial probability distribution of our 2s orbital there, we find that an electron in 2s orbital spends a reasonable amount of time very close to the nucleus. So, when the 2s electron is somewhere here, it does not feel the shielding by the 1s electrons there, because it is slightly farther from there. So, since these electrons are now, the 2s electron can be very close to a nucleus, it feels the attractive influence of the nucleus, and as a consequence the energy becomes less. Whereas, the 2p orbital, though it spends more time relatively nearer to the nucleus, but it does not come so very close to the nucleus, as a consequence the penetration of 2s orbital is lesser than that of the 2p orbital there. So, since 2s orbital is more penetrating, it spends more time near the nucleus, it feels the nuclear charge in a greater way, as a consequence it gets stabilized. And the result of that is that the energy of 2s is less than that of 2p. That is, we remember that we said the degeneration is lifted. When the degeneration is lifted, 2s becomes of lower energy than 2p. If you go further, look into n is equal to 3 levels, you find that same argument here. So, we got a 3s electron there, a 3s orbital, 3p orbital and 3d orbital. You find that s orbitals are more penetrating. You can see that 3s can come, even 3s can come so very close to a nucleus, whereas 3p can come as close as this much only, whereas 3d can't come beyond this on an average. So, we find is here again the same argument will hold together, and we will have the energy of 3s orbital to be less than that of 3p orbital, which in turn will be less than that of the 3d orbital there. So, we find that this penetration effect of these orbitals is a very important or significant reason for the difference in the energies over. Okay. Now, with these arguments over here, we can rationalize the energy level diagram which we made earlier for multi-electron atom there. What have we done so far? What have we done so far is we have analyzed the energy expression what we got from hydrogen atom, and that we saw that how does that translate into an energy level diagram for hydrogen atom. Then thereafter we realized that when we go from hydrogen atom to a multi-electron atom, we find that this energy level diagram changes. We have seen reasons for that. That means the factors which determine the energy of different orbitals there. And in the light of that, now what we have got for a multi-electron atom, there is an energy level diagram there. That means the energy is increasing in a given order there. So, what do we do next is, now let us try to see in case of a multi-electron atom, and then because of hydrogen atom there is only one electron, it occupies only the first s orbital there, 1s orbital, and so on and so forth. If you give more energy to that, maybe it comes to n is equal to 2 level or 3 level and so on and so forth. But our main concern is what happens in case of multi-electron atoms there. In case of multi-electron atoms, what we see that since there are more than one electron, so we have to understand that how do these electrons distribute amongst these energy levels, and that basically is referred to as electronic configuration. So, electronic configuration of atoms primarily means the distribution of electrons amongst the energy levels there. And for this there are 3 rules, very important rules there. One is the Aufbau principle, second is Pauli's exclusion principle, and third is Hund's rule of maximum multiplicity. These you have done at your +2 level also, but still for sake of completeness of argument, I will briefly recall these rules for you. Let us begin with Aufbau principle. Aufbau principle, we know that Aufbau in German stands for building up, and according to this principle, the electrons are put into orbitals in the order of increasing orbital energy. All this is known to you, I will not spend too much of time on this. And what basically we have is this order, so called order, increasing order of energy, is determined by the values of n plus L, because it is a multi-electron atom there. Further, if you just look at this, say a 4s orbital having n plus L equal to 4, because 4s means n is equal to 4, L is equal to 0, total is 4. So, 4s orbital having n plus L to be equal to 4 is filled before 3d orbital. This becomes to third principal quantum number, but this is fourth one, yet this will be filled before this one there, because it is n plus L which matters and not only n. Secondly, suppose there are two orbitals for which both of them, if n plus L happens to be same, in such a case the orbital having lower value of n will be filled first. These are simple rules which you are familiar with. Now, let us see what is Pauli's exclusion principle. Pauli's exclusion principle says that no two electrons in an atom can have the same set of 4 quantum numbers. Let us take a simple example, say of helium atom. In case of helium atom, there are 2 electrons, and for these 2 electrons, what we are showing here is 3 possible distributions there. In first case, both the electrons are in 1s orbital there and having up spin there, that is, the spin is upward there. In this case, one electron is having upward spin, one is having a downward spin there, and in third case, it is both of them are having down spin over there. Now, which of these 3 is a acceptable distribution there? And according to Pauli's exclusion principle, we find that this one is not acceptable, because if you look into this, say for both these electrons there, what do we have? For them, n is equal to 1, because the first shell there, L is equal to 0, s orbital there, m also is 0 for that, and then both the electrons have got plus half as the spin quantum number. Since the two have got same quantum number, so this is not acceptable to us. Similarly, this also is not acceptable, because in this case both the electrons have got spin quantum number to be equal to minus half. So, accordingly, this configuration there, that is this distribution of electrons wherein the 2 electrons, one is having plus half spin, one is having minus half, both of them are occupying the 1s orbital, that means they are anti-parallel to each other. This is acceptable kind of electron configuration of helium atom there. So, as a consequence, we can, from this we can infer that for a given orbital only 2 electrons can occupy, and these electrons must have opposite spins. That is very crucial there, because if they are not having opposite spins, like in this case or in this case, they will not be acceptable, because they will have spin quantum number to be same in both the cases there. Let us move further. The evidence for this configuration comes from the magnetic behavior of helium. Experimentally, helium gas is found to be diamagnetic, and that actually is in accordance with this configuration only, because had it been this or this, the helium should behave paramagnetic, because any system having unpaired electrons are paramagnetic in nature. So, in this case, so what you are finding is, since helium is observed to be diamagnetic, that can happen only if having this configuration, which is what exactly the Pauli's principle predicts to be. Let us move further and talk about the third rule, that is called as a Hund's rule. What does it say? It says that in a subshell, most stable arrangement of electron is the one with the greatest number of parallel spins. Again, a very simple rule which you are familiar with. Let us take a simple example, say of carbon. For carbon, the electron configuration is 1s2, 2s2, 2p2. But the question is, how are these distributed amongst the, say, especially these p electrons, how are they distributed there? Let us look into that. Now, say for carbon atom, again I am taking up 3 possibilities there. So, what do we have? I am primarily focusing on to this p2 part of it, the 2 electrons in the p orbital there. One possibility we have taken up is that both these electrons are occupying the px orbital there. So, one is spin up, one is spin down. In this case, one is in px orbital, one is in py orbital, and both are spin up. And in this case, one is spin up, one is spin down, but they are having different orbitals over there. So, if you look carefully, all these 3 configurations I have shown here, they are in accordance with the Pauli's principle, because in all of them all the 4 quantum numbers are different. But according to Hund's rule, this is not acceptable, because in this case the number of parallel spins, they are not parallel to each other. In this case, they are also, this also is not acceptable, because though they are in separate orbitals there, but they are anti-parallel. So, according to Hund's rule, this configuration here, wherein the 2 electrons are in different orbitals and having a parallel spin. So, that is the crux of Hund's rule there. Let us move further. Let us move further and see that how do we experimentally determine, we have said from the rules, say for carbon this should be electronic configuration, but how do we verify that? How do we find it experimentally that is this the right electronic configuration or not? And for that, the answer comes from what is called as photoelectron spectroscopy. As the name suggests, photoelectron spectroscopy is based on the photoelectric effect. So, what you would do in this case is you take an atom and then you take high energy X-ray photons, and those photons are made to fall on the atom there. So, when the high energy X-ray photons they fall on this, what they do is they knock out the outermost electron from the atom there, and as a consequence, since I am using very high energy for that, so part of that high energy is used to remove the electron from the atom, and rest of the energy comes out as kinetic energy of the electron there, and that kinetic energy is measured. So, kinetic energy, this is what I have measured over there. H nu is the energy of the photon I am giving there. So, this is known to me, this is known to me. So, from this I can just work out what is the value of Be. Be is called as the energy which is necessary to remove the specific electron or binding energy, so to say, and this energy is approximately equal to the orbital energy there. So, what do we do? For a given atom, we take the atom, go on giving photons of high energy there, take out one electron, they give another one, another second also will come, third electron will also come. So, you remove all these electrons one by one, and for each one of them determine the kinetic energy, and since we know that initial energy of the photon I am trying to put over there. So, from the kinetic energy measurement I can work out what are the energy required for these electrons to be removed from there. So, that actually gives me an estimate of the energy of different orbitals there. So, that is the way electronic configurations are determined using photoelectron spectroscopy. Now, let us move on to anomalous electronic configurations. What basically we find is the electronic configuration of most of the atoms, they follow the rules. That means, the configuration predicted by the rules and experimentally observed, they match, and there are a few exceptions there, and two very important exceptions here are that of chromium and copper. In case of chromium, the configuration is found to be 3d54s1. I am talking only about the valence electrons over there, I am not talking about the core which is argon in all the cases here. Now, so the configuration experimentally found is 3d54s1, whereas the rules predicted to be 3d44s2. Similarly, for copper also, what we find is the experimental determination gives us the configuration to be 3d10-4s1, whereas the rules predicted to be 3d9-4s2. And this has been attributed to the extra stability of half filled and fully filled subshells. And let us understand what are these, why are these so called half filled and fully filled subshells of a given shell happen to be extra stable. Let us look into that. Now, for this there are two main reasons. One happens to be the symmetry and second is the exchange energy. We will discuss each one of them one by one. First, let us talk about the symmetry here. So, what I am showing you here is I am talking about p orbitals there. We know that p orbitals are degenerate. There are three p orbitals there, px, py, pz and so on and so forth. Now, suppose I have got only one electron in this p orbital there. It could either be in a px orbital or py or pz. If it is in px, the electron distribution will be something like this. For py, it will be like this. For pz, it will be like this. And all these distributions are symmetric, but to a certain extent only, because this is symmetric along this axis only, this is symmetric along this axis, this is symmetric along this axis there. As against P1 configuration, suppose I come to P2 configuration. In case of P2, say just taken one of the possibilities here, there can be more possibilities there. I am just taken one of them. Say I have taken one electron to be in px orbital, one in py orbital. So, in this case, so this will be a kind of electron distribution over here, which again is symmetric around this axis and this axis. That means, this distribution of electrons is more symmetric as compared to this or any of these things, but still not very symmetric there. As against that, if I come to a P3 configuration, what do we have is that one electron is in px orbital, one in py, one is in pz. So, that is the kind of electron distribution we have. This is much more symmetric as compared to this, which in turn is more symmetric than this distribution there. So, what you find is that when I have a half filled situation like this, that means all the three orbitals having one electron each, this distribution of electron is more stable as compared to that of P2 or P1. Similarly, if you go further, I can come to P4, P5 and P6. So, again we find that when you got P6, all these three orbitals here are doubly occupied. So, this will be more stable as compared to that of a P5 or other configurations there. So, in this way we can see that the symmetry kind of explains the extra stability of half filled and fully filled subshells over there. Now, let us take up the second factor, that is exchange energy. Exchange energy basically is a quantum mechanical parameter with no classical analog, and this actually arises because of the indistinguishability of the electrons and the alignment of their spins over there. And what you find is that suppose I have got a degenerate orbital there, say p orbital. So, there are 3 orbitals degenerate over there, and electrons are present in these 3 orbitals there. So, what can happen is, suppose one electron is like this, second is like this, third is like this. So, what can happen is, I will show you the animation a little later. So, what can happen is that these electrons can exchange their positions. So, this electron can come here like this. That is what is meant by exchange. When they exchange positions like this leads to some kind of an energy is released in the process, and this decrease in energy is called as exchange energy, and this is what contributes to the stability. Let us move further a little. Now, what we have is this exchange energy for a given electronic configuration is proportional to the number of pairs of electrons which can effectively exchange their positions there. And the expression for this is that E exchange, that is, this is total exchange energy for a given electronic configuration, is equal to K into P, where K happens to be the exchange energy per exchange. That means, if there is only one electron pair exchanging, what is the energy released over there? And P happens to be the number of such exchanges which are possible for a given electronic configuration there. So, if there are more exchanges, more exchange energies there, that means the configuration will be more stable. Now, let us take up some examples and understand that. Let us take the example of a P3 electronic configuration. So, what do we have is, I have got 3 degenerate orbitals there, Px, Py, Pz, and I put one electron in each one of them. I have purposely changed the color of these electrons, because all electrons are identical, we know that they are indistinguishable, but I have just shown for the sake of clarity here, that is, these 3 are of different colors there. Now, what can happen? Let us try to understand what kind of exchanges are possible in this configuration there. One possibility is this, that is, the electron in Px orbital and that in the Py orbital, they interchange their positions. So, what can happen is the configuration now becomes this. Second possibility is, that is, this first electron, the electron in the Px orbital exchanges position with the Py electron. Now, the second possibility is that we have got XZ exchange, that means the Px electron and Pz electron, they exchange their positions there. That is the second possibility. The third possibility is, that is, this Y and Z exchange their positions there. So, there are only 3 possibilities there. The first orbital, that is the Px orbital, can exchange positions with Y and Z, Y can change with Z only, and you can't go the other way around, because X has already been taken care of when we talked about the initial first exchange over there. So, in case of a P3 electronic configuration, what do we have? We have got a total of 3 exchanges possible there, and since for each exchange the energy happens to be some value K. So, the total exchange energy for this particular configuration happens to be 3K. Okay. Let us move further and make a statement here, that is, the number of pairs of parallel electrons which can exchange. There is a simple formula for that, that happens to be, that is the value for P you can determine by n into n minus 1 by 2, where n happens to be number of parallel spins there. So, in this case number of parallel spins are 1, 2, 3. Since the number of this happens to be 3, so you can see that 3 into this is 2 divided by 2, 2 cancels out, we have 3. So, that is how we have got 3 possible exchanges there, and as a consequence the exchange energy happens to be 3K for this electronic configuration, that is P3. Let us take the next example here, say P6 electronic configuration. Now, what can happen? In this case of P6, what you see is there are 6 electrons. So, both are antiparallel here, same is true here, same is true here. So, what do we do is we try to understand the exchanges, because for an exchange to take place the spins must be parallel. So, let us now talk about first the spins which are pointing upwards, plus half spins there. So, it is the same as what we had in case of P3. This is one possibility, second one, third one. That means, the 3 spins which are pointing upwards there, say this one and this one, they exchange their positions, and there are 3 possibilities we know of. Similarly, what can happen is the 3 spins which are pointing downwards there, say this one and this one, they also exchange their positions, and what do we have is there are 3 possible exchanges there. So, in case of a P6 now, what you find, there are 6 possibilities there. There are 6 exchanges possible. So, the exchange energy will be equal to 6 times K. Since the exchange energy happens to be more in case of P6, so P6 configuration is more stable than P3 electron configuration. That is a very simple way of looking at the exchange energy and its contribution or explanation of extra stability of half filled and full filled electron configurations there. Now, let us continue our argument and take up the case of chromium, which shows the electron configurations to be 3d5 4s1 as against what the rules predict it to be 3d4 4s2. Let us try to see how do we rationalize that in terms of the exchange energy there. So, what do? We take both the electron configurations and try to work out the exchange energy for each one of them and see which has got more exchange energy. Let us start with what the rules predict, say 3d4 4s2. So, that is how the electrons are distributed over there. So, there are 5 degenerate orbitals here and this is the 4s1 there. And here again I have done the same thing. So, there are 4 electrons there, all spins up there and they are shown of different color for sake of clarity there. Okay. Now, if we talk about the exchanges there, let us look at the first electron here. I have not labeled the d orbitals there. So, let us put it into the first orbital here. This can exchange position with this one and this one. So, there are 3 possibilities there and that is how these 3 possibilities are. That means, this electron which is shown in white can change position with the second one here, the third one and the fourth one here. So, the 3 exchanges are possible vis-a-vis this electron and the rest of them. If you look at the second electron now in the second orbital here, this can have only 2 exchanges, one with this one with this one. So, what we have is that is how exchange is possible here. So, what do we have? So, there are 2 possibilities here. And if you look at this electron in the third orbital here, this can have only 1 exchange with the electron over here. And for this there is no exchange possible there because all the exchanges which this can take place have been taken care of in the earlier cases here. So, what you find is for 3d4 4s2 configuration, we find that there are 6 exchanges possible there. So, the exchange energy happens to be 6K. Now, if I go further and take the second electron configuration which is experimentally observed, that is 3d5 4s1, and now do the same exercise all over again, what do we find? All the d orbitals here have got 1 electron each and all of them having a spin up there, and 1 electron occupies the 4s orbital there. This will not be in the reckoning because all these exchanges when you talk about, they had to be amongst the degenerate energy levels there. So, 3d electron will not exchange positions with the 4s electron there. So, we have to focus only on to the 3d electrons there. So, this electron in the first orbital here can exchange position with 1, 2, 3, 4 of them and so on and so forth. Let us try to see what are the possibilities. So, for the first electron there are 4 possibilities. It can exchange position with the second orbital, third orbital, fourth orbital and fifth orbital there. If I look at the second electron now, this can have 3 possible exchanges here, here and here. So, accordingly there will be the electronic configurations there. For the third possible electron, there are 2 possibilities. That means, you can exchange with this orbital or with this orbital. For this one, there is only 1 possibility, and for this electron, there is no possibility at all. So, what you find is there is a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, 4 from this 4 plus 3 plus 2 plus 1, that makes it 10. So, there are 10 exchanges. Since there are 10 exchanges, so the exchange energy happens to be 10K. That means, this electronic configuration has exchange energy of 10K, whereas the previous one, that is 3d4 4s2, had an exchange energy of 6K. Since for this electronic configuration the exchange energy happens to be more, so this configuration is more stable and also experimentally observed. That is, the electronic configuration what you observe for chromium is argon 3d5 4s1 and not the expected configuration of Ar 3d4 4s2. Similarly, we can extend our argument and talk about the case of copper, where Z is equal to 29. Here again what we do is the same exercise, we will not do it that elaborate way, but what you can see is, say if I have got this electronic configuration argon 3d9 4s2, for this how many exchanges are possible? Now we can just work out without getting into details of that. What you see is that if I look at this d orbital here, in case of d orbital here, so there are 5 orbitals, 4 of them are doubly occupied, 1 is singly occupied. And if you look in terms of the spin's nature, so all the 5 orbitals have got spin up electrons in them. So they can exchange positions with themselves. So there are 10 exchanges possible for them. We just saw it in case of chromium there. And when we talk about the exchanges with respect to the spins which are pointing downwards, we find that there are 6 exchanges possible, what we saw in case of chromium's 3d4 configuration there. So there will be a total of 10 plus 6, 16 exchanges there. So exchange energy will be 16K. Now let us take the second electronic configuration, that is 3d10 4s1. So what we see is for this electronic configuration now, so this d orbitals here, so all the 5 d orbitals are doubly occupied. That means there are 5 up spins there and there are 5 down spins there. So what we can do is, when we talk about exchanges, we can first talk about the exchanges amongst the up spins there. Since there are 5 of them, so there will be 10 exchanges possible for that. And when you talk about the down spins there, since there are again 5, so they can exchange and they give me 10 possibilities there. So the total possibilities will be 20. So in this case there are 20 exchanges possible, the E exchange will be equal to 20K. Since the exchange energy for this electronic configuration is more as compared to that of this electronic configuration, we find that the stable electronic configuration of copper happens to be 3d10 4s1 because of the higher exchange energy. Let us sum up what we have done today. What we have done today is, we started by reviewing the contents of the previous session. Thereafter, we discussed the energy level diagram for hydrogen atom and that of the multi-electron atoms there. Thereafter, we discussed the rules for determining the electronic configuration of atoms. We talked about the Pauli's principle, Aufbau principle and Hund's rule and all. Thereafter, we talked about, very briefly, we discussed about the method for the experimental determination of electronic configuration, wherein we brought in the photoelectron spectroscopy. And thereafter, we outlined certain anomalous electronic configurations, typically that of copper and chromium. And then we explained the stability, because these anomalies are attributed to the stability of half filled and full filled orbitals there. So to rationalize that, we explained this stability part in terms of exchange energy and symmetry as well, but primarily the exchange energy there.